All right, so basically the final section of Unit 4, L'Hopital's rule and a little bit of related rates if we need to add that in. L'Hopital is actually kind of a cool thing. It's using derivatives to make limits better. So before, in our initial chapter when we were learning about limits, we didn't know derivatives yet. Derivatives actually can circle back and help us with limits. So L'Hopital made this rule. So it's the idea of if you're taking the limit of a quotient, you can actually, instead of doing that limit, you can do the derivative of the numerator with at a and the derivative of the denominator at a. And if you divide those things, it's the same thing as the limit. Neat. This is really cool for when we can't find the limit using normal methods, and it's just straight up easier sometimes to do this method. If that doesn't quite work, there is also an additional form of L'Hopital's rule where instead of just dividing those two things, you actually take the limit as x approaches a of that numerator and denominator relationship. But by taking the derivative, you could potentially make that limit easier than if you took it in that original form. Note that we're not doing the quotient rule for this thing. It's different because before, when we were doing the derivative of a whole thing, of a whole quotient, it was the whole quotient was f of x. We're just going to treat that numerator as its own function and that denominator as its own function and just take the derivatives of those pieces, as opposed to treating the whole thing that's inside of the limit as the thing we're taking the derivative of. Just the derivative of the numerator and just the derivative of the denominator. So we're going to try this out. So our old method of finding this limit, we talked about this way back. Oh, dang it. Crash. Laptop, you've been actually pretty good. I've been recording videos for a little while, and that was the first crash that it did. So you've been doing pretty good. That's okay. You can crash. Anyway, when we did these back in the day, way back in Unit 1, what we did is we needed to rationalize the numerator for this problem. So we multiplied by x plus 10 plus 4 to the numerator and to the denominator. X plus 10 plus 4. So we ended up with the limit as x approaches 6. And we couldn't do that right away because then we'd have a 0 in the denominator, and we can't have that. So in the denominator, we would just kind of keep that x minus 6 as is, and then we would keep the square root of x plus 10 plus 4. And then in the numerator, we were able to square that first thing, so we get x plus 10, and then square that second thing, so that's 16, and we just slap a minus in the middle of those. So we end up with the limit as x approaches 6 of x minus 6 over x minus 6. Let's see if I can write it decently this time. Square root of x minus 10 plus 4. And then we're like, oh boy, those things cancel. So it's the limit as x approaches 6 of 1 over our square root of x plus 10 plus 4. And then we were able to do direct substitution. So it was 1 over the square root of 16 plus 4, and we got 1/8. Hooray! Wasn't that lovely and tedious? Well, enter L'Hopital's rule. What you can do is, instead of all that garbage, you can use L'Hopital's rule to help you out. To do that, you take the derivative of the denominator. So derivative of that denominator is just 1. And then you take the derivative of this numerator, and we're going to find that at 6. So that is oh, sorry. That's going to be 1/2. Come on. 1/2 of 6 plus 10 to the negative 1/2. And that 4 goes away from the derivative. Okay, so then that 6 plus 10 to the negative 1/2, that's got to go in the denominator. So now I've got 1/2 over the square root of 16, which is 1/2, 1/2 over 4, which is 1/8. And we're done. And that's it. Oh my gosh, you're so cool, L'Hopital. You're my best friend. I love that. Let's try another one. And now we're not going to do any of that old nonsense. In fact, actually, this one we have no choice. In this one, it was just like, well, I can't put 1 into the sign because the sign of pi is, once you put 1 in there, sign of pi is 0, and we can't have 0 in our denominator. So, dang it, we just can't find the limit of this one. I'm sorry. Maybe we'll look at the graph or something. Well, now we can because we have our good friend L'Hopital. So we take the derivative of our numerator at the value we're taking the limit of. So we need to find the derivative of ln, which is 1 over x, but instead of x, we're taking the derivative at 1. Then this is going to be over the derivative of sine, so we got to take the derivative of this, which is derivative of sine is cosine. But I don't want to do it at x, I want to do it at 1. But I do need to follow the chain rule, and I need to do the derivative of the inside. So the derivative of the inside is going to be just pi. Okay, a little bit of quick cleanup. That numerator becomes 1. The cosine of pi is 1. No, negative 1. Ah! Times our pi. So our limit is 1 over pi. Well, negative 1 over pi. Limits are so easy now. Oh, they're so easy. Thanks, L'Hopital. You're great. Okay, now one of the reasons that we need to use L'Hopital's rule is depending upon, we really need to be using it when things are not evaluating correctly. In case this one, we're trying to find the limit as x approaches infinity, and we can even use this with infinity rules. So we get, in part A, we're deciding what kind of thing that we're not allowed to do. So this one is the limit as x approaches infinity of x to the 1 over x. Oh. When you do direct substitution, you substitute in infinity for both of those x's. So we get infinity to the power of 1 over infinity. We got 1 over infinity, that's basically 0. So we get infinity to the 0. We can't evaluate that. And in fact, L'Hopital right now is not going to be able to do anything for us because we don't have a fraction. We don't have something over something else. So let's manipulate this a little bit so we can use our good friend L'Hopital's rule. This limit equals some number. It equals that gross infinity to the 0. So I'm just going to replace that with a y. Once I've got that, I can take the natural log of both sides. The idea is I want to try to get that 1 over x out of the exponent. So I'm going to take the ln of both sides. So I've got the ln now of y equals the ln of the limit as x approaches infinity, x to the 1 over x. Now, since I'm taking the ln of that limit, I can just bring ln inside of that limit because that's where I really want it to do its business. I'm going to stop writing the left-hand side because I'm not going to do anything with it anymore. It's just going to kind of stay that ln of y. I'll bring it back in a minute. So we want the limit as x approaches infinity of the ln of x to the 1 over x. Because if we're taking the ln of a limit, that's the same thing as taking the limit of the ln. I hope that kind of makes sense. All right, now that that x to the 1 over x is inside of a natural log, we can use our rules of logarithms and bring this 1 over x, bring that exponent in front of the natural log. So then we have the limit as x approaches infinity of the ln of x, ln of x over x, because it's a 1 over x, and the x drops to the denominator. Yes, L'Hopital, L'Hopital. Now we can L'Hopital it because it's nice. It's a one function over another function. So this equals the derivative of the denominator. So the derivative of the denominator is going to be just 1. Derivative of x is just x. And then the derivative of our numerator is 1 over x, but evaluated at that particular point. So that's 1 over infinity. So this just equals 0. Because we have 1 over infinity, that's basically 0, over 1, that's 0. Sweet. All right, now let's bring in that other side now. ln of y. I don't want the ln of y. I want to figure out what this derivative, I want to figure out what just y is, not ln of y. So to solve this thing, I'm going to just change the language. So ln of y is e to the 0 equals y, if I convert that back into exponential form. And e to the 0, that's just 1. So our limit should be 1. And you can even see that. I've had this graph up here the whole time. But as we're approaching infinity, this thing is getting close to, from the top, it's coming down towards that 1. So as we're getting towards infinity, it's kind of coming down from above. It kind of goes above it and then comes back down to meet at 1. And that's it. So that's L'Hopital's rule. There are 2 versions of it. I was mostly doing that first version of it. There are times where you need to do the second one, where after you take the derivative of the numerator and denominator, you still can't find the limit. So then you just kind of, you can't divide those 2 things, I should say. You can't divide those things, so you check the limit of where those 2 things, when you divide them, are heading towards. Oof. It's a rough sentence. All right, that's it for Unit 4. I have one more video for next time. That's just like one more of those particle motion videos, just so that you can see one more example of those. But mostly next time is going to be your presentations. Well, the time after the time that you watch this one before. You know what I mean. You know what I mean. Have a good day. Bye-bye.